So last time we started this ith smallest element in a given array of size n. Right, so you can immediately solve it by sorting, but we want to give a super clever linear time algorithm. It's an incredible demand. So our subroutine will be, the function will be called select s comma I. S is the n size array and I is the ith statistic that you want. And so mainly it has two inspirations. First is the quicksort recurrence idea, that you divide into two parts by pivoting and then recursively call on those parts. And so what kind of recurrences we are dreaming, that we have to first fix. So example 2 is what we want. We want something like 20% is the first part, the remaining part 80% don't use full, use only 70%. Okay, and since this 20 plus 70 is not 100, this recurrence will be a linear time algorithm. So we'll try to get to this recurrence. Second is what pivot will give you this property. So that pivot will be approximate median. Okay, so the thing in blue is important. So we want a pivot so that less than equal to x elements are some fraction of n, at least, and also greater than x are the same fraction at least. Okay, so in other words, this elements smaller than x are in the range bn times bn comma 1 minus b times n. I think b in our case will be 30%. We will see. So this is so the range is basically 30% to 70%. That's the leeway for your approximate median. So once we have a way to find this pivot, we have written a pseudocode. So assuming that you have this x, b approximate median by some simpler algorithm. So it will basically be a recurrence recursive algorithm where we'll just make one call. Okay, so one call will be against some fractional part of n. So it will be order n plus t of d times n. So you do the partitioning according to this x, so you get s less than equal to x part and s greater than x part, and then you have these three cases. So if the first part is I, size is I, then you have found your answer. Pivot is the answer. If the first part is big, then you just forget the second part, go to the first part. And third is, if the first part is small, then forget the first part, go to the second part. Right? So all three cases are covered. And the recurrence is this. Is this clear? Okay. So then we will do the really clever part, which is how do you find this approximate median fast? So notice that we have a flexibility in picking d and 1 minus d and b. We have not fixed this yet, right? So we'll fix it, or we hope to fix it, such that d plus 1 minus b is smaller than 1, right? So in particular, d has to be smaller than b. This is what our ultimate fixing will be. So yeah, any ideas how to find this approximate median? Is there a magical fraction b which will help you compute the approximate median x by a single recursive call? So the idea here will be reduced to exact median. Okay, so what that means is you have this S and you want to reduce it to some other instance M such that the B approximate in S corresponds to exact median in M. So you want to map B approximate, in fact you want to have a bijection between B approximate and exact median. So any ideas how can you reduce approximate median to median of a different set? And then since the question will be on the median of M, we can call select M there. Select M comma size by 2 will give you in one recursive call the answer. Right, so how do you do this? So idea 1 you have seen, so now that's the last idea. So we break S. So we want to break S into sets whose median you can compute very fast, which means that how big should these groups be where you can compute median by brute force? So they have to be significantly smaller than n, something, let's say square root n, right? If you take a square root n sized array, then you can sort it and you can compute the median. Everything you can do in order n. So the groups have to be significantly smaller than n. So in fact we will keep it a constant, so we will keep it 5. So let us break S into, let's start with something simple, into sub arrays of size 5. So these will be how many? N by 5 many. So just go over the array and at every 5 you call it a subarray. So you have n by 5 subarrays, and for each subarray you can compute trivially the median in constant time for each. So in linear time you have computed all these medians of the n by 5 subarrays. So compute, so let's call that M. So M is the set of their medians. Right, so now you have n by 5 medians, and what should you do? So obviously you should take median of median. Right, so that's the last step. You take the median of these medians. Okay. So break up into groups that are very small, so you can trivially compute the median and then find the median of median. That is my pivot X. So the question is, why is this, what kind of a B approximate median is this? Right, this is the property you want to prove now, or even discover. So can you see this already? What is the property of X? if you take median of medians in an array. Okay. If you don't see it, then you have to work hard. So let us draw this picture. So I'll draw or I will rewrite S array in terms of this 5 cross n by 5 matrix. So this is the first column, then we have a second column, and so on. And somewhere here sits your x. Okay, and these are the medians. And this is sorted, increasing order. So I can look at this array as 5 cross n by 5, where each sub-array is just a column. And then in our mind, we have just sorted this according to the median array M. Okay, so before x, I will see, I mean, you cannot do this algorithmically because it will be expensive, but this is how I am drawing the diagram, that this M is here, suppose this is just sorted schematically. So we have actually found this array M in unsorted way, but I am drawing the picture as if this M is sorted. So all these red dots before are less than x, and the dots above are greater than x. And how many are they? Half of n by 5, right? Because x is the median in M. So this is, let's say, n by 10. This is the first column, second column, n by 10th column, and n by 5 column. So columns are numbered from one index from 1 to n by 5, and the middle one is n by 10, where the median x of M sits. And this red part we are assuming sorted, increasing order. So this we are drawing just to see the size of the number of elements in S which are smaller than x. How many are they? You want a lower bound. So clearly, this blue shaded part, do you see that every element here is smaller than x, right? Because the previous red dots, they are all smaller than x. And then when in a column you see the blue part will be smaller than the dot, red dot, right? Because the column is also sorted. So this blue part is the less than x part. And similarly here the green part is greater than x part. Right, so what we have learned is the following, that if I look at less than equal to x In fact, this also is included. So this blue part gives you a lower bound of greater than or equal to 3n by 10, right? So 30%. So this X is so beautiful that at least 30% of elements in S are smaller. And symmetrically the green part. Okay. So which means that X is a 30% approximate median. Is it fine? So yeah, so you have your like the hard part is now done. So you have identified your pivot, right? The pivot by one recursive call, you can actually compute the pivot, which will be 30% approximate median. What we have to see is now the recurrence. What are these D and B? So this is the median of the whole set array of S, not M. For M, X is exact, but for S, X is approximate. Any questions on this slide? Okay, so now what we will do is let us fix the constant. So what is D? D is one recursive call which you will do to compute the approximate, to compute X, right? So that will be basically the coming from the size of M. So this is the size of M upon size upon N, which is 1 by 5. And B will be, which you just saw, 3 by 10. Okay, so in the previous description, the B you get is 30%, the D that you get is 20%. And this means that the recurrence is for select code is Tn less than equal to order n plus n by 5 plus, what is the other part? If B is 3 by 10, the other part is the other bigger one, so 7 by 10. And you have to notice that 1 by 5 plus 7 by 10 is less than 1. Okay. So we have the hallowed recurrence, which will give you Tn equal to order n. Okay, so this finishes the IH statistic theorem. By who? So there were 5 people, BF, P, R, T. So select S comma I finds the ith min of S in linear time. Okay, so it can find obviously the median in linear time, in order n time, but it can also find anything you want, any ith. Any questions? Okay, if you have no questions, then you should go home and do this exercise. Why did we pick 5? Why not 3 or 7? Okay, in fact, why not something even also? So why not 4 or 6? Okay, so why did I start with the group of 5? So that you have to see that 3 and 4 will not work. You have to try with 5, and with 5 fortunately it works. Okay, so that is not clever, but just like trial and error. You try all these, one of them works. Yeah, so natural thing would have been to just take 3 cross n by 3 matrix, because for 3 also you will find the median, and then do this calculation and see what happens. So the trick is that ultimately you want to match D and B, D plus, so D will be, if you take 3, then D will be 1 by 3, but then there will be a problem with B. Okay, you want to balance those inequalities. Okay, any questions? Yes. How that is happening? So that was in the last class. That was here. So let's compare. So the pseudocode we are analyzing is this one, select S comma I. So which step is unclear? Yeah, so what is the complexity of select S less than equal to X? And what is the complexity of select S greater than X? So for one, the complexity, I mean by the guarantees you have from the, so that was in the definition of approximate median. So on the top right slide, you see that the guarantee is between Bn times 1 minus Bn. So the bigger one is 1 minus Bn. So whichever case this select Si calls, and remember that it will call only one, not both. Whichever it calls is smaller than 1 minus Bn. So you have Dn and then you have 1 minus Bn. These are the two calls. And interestingly, they are almost independent. So this D and 1 minus B are independent. So you have some flexibility. So this degree of freedom you use in a creative way to actually fix them. That works. Is it clear? Okay. Yes, so that is already a surprising thing, and now you will see even more surprising things, because now we'll start a new topic called greedy algorithms. So this topic has the property that it will be full of very simple algorithms, but when I will ask those questions in the exam, they will be very hard to solve. Okay, which you have seen many times before also, but here it will be especially hard, because in the class, whatever algorithm you will see, it will look very simple. It will just be sorting. but you will never know in the question what are you supposed to sort with respect to what. And giving the proof will always be tricky. So this paradigm is called the greedy paradigm. We'll see many examples of it. Some of them are major algorithmic results. They are even present in your programming assignment, I think. You have to use greedy paradigm. So yeah, we'll dedicate much of the remaining time on this. So we begin a powerful paradigm. In algorithmic design. And also true, it is also true for human history. It's always very difficult to actually know what should you be greedy for. Okay, if you are greedy for the wrong thing, then you will lead to a suboptimal result. If you are greedy for the right thing, you will lead to an optimal result. So that problem you will see all the time in our questions. It will never be clear that should we be greedy, and if we should be greedy with respect to what. Okay, but when you do it right, it's very powerful and gives very simple algorithms to implement. So it's a bit confusing with respect to the divide and conquer paradigm. So I have to write how it is different. And then you have to revisit these steps. So usually what happens is you divide the problem into smaller parts. Okay, so these parts should look, the question should look the same as the original question, sub-problems. So you divide your problem into sub-problems, which obviously you have already done in the divide and conquer paradigm also. So how is it different? So mainly the difference is that it will not be a recursive algorithm, it will just be an iterative algorithm. So you divide into smaller parts, and in each part, pick the best local solution. Okay, so in that small locality, you find the best solution, and then show that this solution that you have found is actually a global solution also. The best global solution. Okay, so this part will be much easier to implement than what we do, for example, in merge sort, where even the merging part is non-trivial. So usually that part here will be trivial. So these will not be recursive calls, but just you solve it part by part locally, and then a global solution emerges out of that. But the proof you have to give. The proof is always non-trivial and very hard to see that it works. So it will be very soon it will be evident. Let's take an example for that. So the problem of job scheduling. Okay, so here the problem is, as the name suggests, that you are given jobs which are to be done batch-wise on a server, on a machine. So you have to create a schedule so that you can schedule the maximum number of jobs. so that their number is maximized. Okay, so jobs will have a schedule, will have a demand in the sense of from what time to what time they will run. Okay, that is not up to you, so that will be in the input. So given the preferred schedule of each job and given one machine only, so you cannot do parallel processing. So two jobs cannot overlap on the machine. You have to make a schedule so that maximum number of jobs are done. So this is obviously practically very useful. I mean, this is just one abstract example. This has many versions. Right? Similar thing you can do for how to schedule classes, how to schedule courses in a single class like L7, and how to assign even students across courses, and so on. And you can also extend this to multiple machines. So you can schedule the jobs first on the first machine, and then the jobs that remain you can schedule on the second machine, and so on, right? So this will be applicable in many situations. So let's specify the input. So input is set J of jobs where what Ji represents is a timeline. So Ji has Si to Fi time, so start and finish. Okay, so what is the hour at which Si will start and the hour at which ith process, ith job will finish, right? So this tuple is provided for each ith job, and a single server is there. But only one at a time. So obviously, once the deadline or the start time is missed by the server, then the job cannot be executed. Okay, so either you have to start exactly, the server has to start exactly executing ith job at Si, or it has to forget ith job, move on to the next possibility. So that is the interpretation of the input. In the output, okay, so what is the maximum number of jobs that output a schedule which covers maximum number of jobs? Is this clear? So any ideas how you will solve this? So the difficulty here is that there are n jobs and the number of subsets is 2 raised to n. Right? So if you try doing this by brute force, then it will be very bad. To try all subsets and see their feasibility. Or validity. So the problem is that time taken will be 2 raised to n. Because you have to go over all the subsets, and checking validity means, testing validity means that whether if I schedule these jobs, let's say J1, J2, J3, J4, is this even possible? So they should not overlap, right? Their start finish should not overlap. Their interval should be disjoint. So that is the question of testing validity. And you have to do this 2n many times. After that, you can pick the maximum, the best schedule. Right? So that is brute force. That's completely, I mean, it is not only impractical, it's impossible. With 100 jobs, 1,000 jobs, this is 2/1000. Right? So this will never work. Never even give you a schedule. So let's define this non-overlapping jobs. That we'll keep using it. So for ith job, we say that J is in, or K is in overlap J comma I. If the interval for I and the interval for K is non-empty. Okay, so this defines what does it mean? What do we mean by overlap? So the jobs which overlap with I, they are the ones whose intervals have an intersection. Okay, and other ones we'll call, so J minus overlap are the ones that are non-overlap. Fine? So this is what validity, which is important to check validity. Yes, so let's now see a big example for this. So this is the timeline, starts from 0. Okay, too little. Okay, so these are, say, the seconds or milliseconds, whatever, 0 to 12 in the timeline, and you are given in the input the job intervals. So this is the interval for J1, 0 to 2, 1 to 4, is J2, 0 to 11, let's say, is J3, J4 is 3 to 6, J5 is 6 to 10, J6 is 8 to 11, J7 10 to 12, J8 6 to 9, and finally 5 to 7. Okay, so these are the 9 jobs with their respective start and finish information in terms of seconds or milliseconds in the timeline. Okay, now your job starts. Out of J1 to J9, what is the maximum you can schedule out of these 9? What is the max? Sorry? 4. How do you get 4? J1, then J4, J5, J5 and J6, J5 and J7. Yeah, so which is already drawn there, right? So that line seems to be the best. Now what you have to show is it is the best. What is the proof of that? There is no better option. So this is what will happen in greedy algorithms, that in the example you may see it fast, but then proving it will be very tricky, especially when you don't even know n. Okay, so let us try several strategies. So let us try the policy. So what he has done by looking at it, let us see how a machine will think about this, right? So what are the heuristics that a machine can try? So policy 1 can be pick the earliest start. So if you pick the earliest start, then the machine may pick J3, right? Because J3 starts at 0. I mean, J1 also starts there, but the machine may not look at anything else. It may just look at the earliest start and pick J3. So J3, the problem is that it will run for so long that it will kill all other possibilities. So after J1, J3, you cannot schedule anything else. Right, so that's a problem with this policy. Let's try a different policies. So early start doesn't work, so maybe it will be more clever to look at the duration. Right, so let us try that. That looks promising. Shortest duration. So first was S, second is F minus S. Right, so so if you want to, the machine wants to first pick, or the algorithm wants to first pick the least F minus S, then how will it go about? So J1, yes, J1 is not a bad option. So you start, machine picks J1, then J9, and anything else? Yeah, so you only have 3. Right, so J1 is the shortest, and so what we are doing here is we are checking validity. So you pick and then check validity, right? So you pick J1 because it is the shortest. But then the validity will tell you that now J2 and J3 are invalid because they overlap with what you have picked. So you delete them. Next, what remains, you pick the shortest, which is J9. Right? So you schedule J9, and that will kill J8 and J5. So then shorter one will be J7. Right? So and then you are done. Then you cannot add any, you cannot schedule any further jobs. So this also is bad because you know that there is a solution for 4. So what is that policy that you use to get to this answer? What do you think? Sorry? Least overlap. Yeah, so unfortunately we don't have time to schedule your job. So let me leave that as an exercise. Yeah, so least overlap is also a valid policy. You should test it, what it gives. This also will not give you a complete solution. Yeah, so the fourth policy that we will try, or in the class it's policy number 3. So this will be earliest finish. Okay, so I mean, it is at this point not clear why this will be the best, because intuitively shortest duration makes sense because you want your server to spend the smallest amount of time per job, but that doesn't work. Least overlap will also not work. So earliest finish is a interesting thing. So you want to first pick the job which finishes the earliest, and after that you look at the remaining valid jobs and see what will finish earliest. Okay, so with that policy, what should you pick? The answer which you said, so J1, you will pick J1 because that finishes first. Then J1 invalidates J2 and J3. So next will be J4. That invalidates J9, J8, you will pick J5. Sorry. J8, sorry, yeah, I have J8. 1, 4, 8 and 7. I see, okay. So this is a bit different from your solution, but the count is still 4. Yeah, so you can see that that's a good example that you have two optimal solutions. I don't have a good explanation policy for the one you said, 1457, but there is a perfect explanation for 1487, which is equally good. Okay, and we'll give an algorithm for this. You are changing the example to what? Between 9 and 10, okay. Taking J5, okay, fine. Yeah, but you can change this obviously in infinitely many ways, but for some reason this policy 3 will always work. Okay, so the question is, why will it work? So is there a counter example for this? So fortunately there is no counter example because I have a proof. Okay, so the proof will be in 2 lemmas, thing which we have to do tomorrow, next time. So, and this will be the template for greedy algorithms and their proofs. Okay, so the template is once you have fixed your policy. Now, always your challenge in the exams and assignments will be that there will be many policies. You have to go over all of them in your mind, pick the best one, then check whether it works. So this sequence of counter examples and proofs, and even to invent the policies, all this makes it very complicated. Okay, but once I tell you the policy, then your bulb should light up. Then it should get easy. Okay, but I won't tell you the policy in the exam. So your job will be very tough. So in this case, since I have told you the policy that focus on earliest finish, so you know that the first one, the first one is you sort finish times in increasing order and pick the first job. Right, so that is my job X. That has to be there according to the policy. So let X be that. Be the job with least Fx. So this is the, in order of finish times, this is the first job. Then there exists an optimal solution S with X in it. Okay, that's what we are claiming. So why is this true? I can pick X and then I remove the jobs that are invalidated, that overlap with X. And there will be a way to finish this process. Okay, that's what we are claiming. So the proof will be, you can say, by contradiction. So let, in fact, not contradiction. This is almost a constructive proof. So let S prime be a different. So we'll do it tomorrow then. Next time. We'll pick S prime to be some other optimal solution. With Y being the least one. Okay, and then we will show how to transform S prime to S without losing anything.